Hello juniors, today we're going to continue with electronic assignment 38, which is about exponential functions. If you remember from last video, we have seen the definition of an exponential function. We have seen real life applications of exponential functions. And then we've made some investigations in order to know how the exponential function looks like. Remember, we had two types of exponential function. We could have either exponential growth or exponential decay in case the y variable decreased as the x variable increased, right? And then we have seen some properties in how to apply the different types of transformations we have already seen to exponential functions. You see that the transformations are exactly the same as the ones we have seen in the first chapter we have covered at the beginning of this year. And what we have to do now, well, we have seen characteristics of exponential growth, domain, range, y-intercept, asymptotes, and so on. And we've seen the same thing for exponential decay. And what we have left to do today is do some examples for you to see how to work with exponential functions. And I'm also going to be showing you how to correctly use your calculators whenever you are allowed to use your calculators to solve some problems involving exponential functions. Okay, so this is example 5 of the book. For this chapter, it says, consider the function y equals 2 to the power of x plus 3. This is obviously an exponential function because we have the variable x in the exponent. So it says, for part A, find the y-intercept and the equation of the asymptote. So first thing, if we want to find the y-intercept, we know that the condition y-intercept, we know that the condition is that the x value should be equal to 0, right? So if we set x to 0, we would have y equals 2 to the power of 0 plus 3. Any number to the power of 0 is always 1. So we say that y is equal to 1 plus 3. So the y-intercept is the point right here. Y-intercept has coordinates 0, 4. Okay, this is the y-intercept of this graph. Then we're asked to find the equation of the asymptote. For the asymptote, if you remember what we have seen here, let me show you here in this case, for example, you see that the asymptote, whenever we have the parent function a to the power of x, the asymptote is always y equals 0, right? But in this case, what do we have? 2 to the power of x plus 3. If it was only 2 to the power of x, if I eliminate this part, then the asymptote would have been y equals 0, right? But since there is this plus 3, remember the plus 3 is causing a vertical translation 3 units up, right? So the horizontal asymptote should also be displaced 3 units up, right? Horizontal asymptote. So the horizontal asymptote in this case is the line y equals 3. Instead of being y equals 0, we displace the horizontal asymptote 3 units up and we get y equals 3. Remember, you should always write y equals and the value for the horizontal asymptote. And there's no vertical asymptote for an exponential function. So that's it for part A. Then we have part B, which says state the domain and range of the function. Okay, so if you remember from a normal exponential function, that means a parent function, like this one, the domain are all real numbers, right? Here it says all real numbers. And for the range, we're only considering the positive values, right? The exponential function never crosses the x-axis towards the bottom, right? So the range is all positive real numbers. So in this particular case, where we have a vertical translation 3 units up, the only thing that changes is the range, right? The domain is still x belongs to all real numbers, right? Because it still covers all the values in x. But the range Remember, it's always associated to the asymptote, right? If the horizontal asymptote is y equals 3, then this means that the function will never cross the horizontal line y equals 3. And that means that the range should be y greater than 3, okay? And y belongs to all real numbers, right? That means that y can take any value which is above 3, okay? And obviously this is not equal to 3. It's only greater than 3 because y equals 3 is a horizontal asymptote, okay? So this is domain and this is range. Done with that. Then for part C, it says sketch the graph of the function showing the asymptotes as a dotted line. Okay, since it says sketch, we can do this, we can do just a sketch. It doesn't have to be very precise. So I'm gonna do the axis first, y and x. I'm gonna leave some space for the negative values here. So this is x, this is y. Since we have found the y-intercept, maybe that's an interesting point to plot on the graph. Let's say that this is 1, 2, 3, 4, and so on, right? Since it's a sketch, I'm only putting those values. So 0, 4 is a known point of the graph. And we know that the horizontal asymptote is y equals 3. So I'm going to do that as dotted lines. I'm going to do green line. So y equals 3, dotted lines, and we get the asymptote. And that's it. So now we can do the sketch, right? We know that this is exponential growth, right? Because the exponent is positive and the base is a number greater than 1. So that means that we will have an exponential growth. So if I go to the graph, I only will do something like this by hand, right? In order to represent the exponential growth. Maybe something like this, and then this goes increasing. Something like that would be fine, right? So this is the equation, y equals 2 to the power of x plus 3. So it's very important to always mark the y-intercept and the horizontal asymptote. Okay, finally, for part D, it says, using your GDC, so here we will need our calculators, solve the equation 2 to the power of x plus 3 equals 2 plus 3 to the power of negative x. So let me write that here. 2 to the power of x plus 3 equals 2 plus 3 to the power of negative x. I think it was like that. Yes. So if we want to solve this, there's no way, well, actually there is a way, but you still do not know how to do that, and you don't need to because you're allowed to use calculator. But it's very difficult to solve this without using a calculator. If we use a calculator, it's actually pretty simple. How do we do that? Let me show you. I'm going to write some steps here first. So using GDC, we're going to graph both functions. And we're going to find the intersection point. So that's all what we're going to do for this part. Let me take this a little bit down. There. So I can put the graph. Okay, so if we go to the calculator, we're going to go to menu graph, menu 5, and we're going to plot both functions, right? The one on the left and the one on the right. The one on the left was 2 to the power of x plus 3, and the one on the right was 2 plus 3 to the power of negative x. Obviously, we need to write this as separate functions because we want to graph both and find the intersection point. So after plotting both functions, we click on draw, F6, and there you have, right? If you're not able to see this correctly, you should go to Shift V Win and change. Maybe you could put like it is here, right? From x min would be negative 10, x max would be 10, and the scale 1. Y mean, same thing, negative 10 to 10, scale 1. Then you draw, and here you have The blue one is the first function, the exponential growth, and the red one is the second function, the exponential decay. So we want to find intersection point. So we go to Shift G solve F5 and intersect, which is F5 again. And there you have the solution of the equation, which is we only stay with the x value, which is x equals 0. Let me write that down. X equals negative 0.4. This would be 490, right? If we write to three significant figures, so that'll be the solution of this graph, of this equation. Sorry. So if we go back to the assignment, this is the answer. X equals negative 0.90. Okay. Super. And I'm going to put the graph later on here for you to have. Let's go to example 6. I'm going to put this down here. This, once again, is using calculator. So it says, the value of a boat y in thousands of UK pounds is modeled by the function y equals 20 times 0.85 to the power of x, where x is the number of years since the boat was manufactured. So, part A. Find the value of the boat when it was brand new. Brand new, what does it mean? That the year, that means that the x must be 0, right? Brand new means, let me write this, brand new is that x is equal to 0. So that's what we need to do first. Set the x to 0, and this would be 20 times 0.85 to the power of 0. Any number to the power of 0 is 1, so this is 20 times 1. So y is equal to 20, and here we're talking about 1,000 of UK pounds. So thousands of UK pounds. Right? So that's the value of the boat when I just buy it. Okay. Super. Then we go to part B, where it says, estimate the value of the boat when it is 3 years old. Give your answer to the nearest pound. Okay, so 3 years old, we need to change the x value for 3, right? So y is equal to 20 times 0.85 to the power of 3. And with the help of the calculator, we can do this. Let me see, this would be 20 times 0.85 to the power of 3. I get a value of 12 point, if I round, I'm going to write the exact value, 2825 thousands of UK pounds. So you see, there's something interesting but real here. As time passes, what happens to the value of the boat? The value of the boat decreases, right? It's getting less worthy. I don't know what's happening here. Less worthy than it was when it was brand new, which is something completely logical, right? Something that occurs in real life. Okay. So you see that although we have a positive exponent, we're talking about exponential decay. And why is that? That is because this base is a number which is less than 1. Whenever the base is a number less than 1, we're talking about exponential decay as well. Okay. Finally, for part C, it says, use your GDC to estimate when the value of the boat will be worth half its original value. If the original value was 20,000 UK pounds, then half of that value would be 10, right? So we need to set the equation to 10. 10 is equal to 20 times 0.85 to the value of x. So we can solve this, right? If I take the 20, well, we will have to use our calculator anyways, right? So don't worry, I'm going to show you how to use calculator for this. So if we want to find the solution to this using calculator, what we need to do is the following. Let me show you. Once again, we would go to the calculator. You should be able to see it right now. So we're gonna go to menu, graph once again. We're gonna erase this, we don't need them anymore. And as our first equation, we're gonna write 10, right? Only 10. That's the equation of a straight line. And for the second equation, we're gonna write the function that the problem gave us. 20 times 0.85 to the power of x, okay? Enter, and we draw this. So we cannot see this clearly, so I'm gonna go up a little bit, and there we can see. You see that the red function, which is the exponential function, is an exponential decay, right? It's decreasing its value as time passes. So when will it be worth 10,000 UK pounds? Here, right here, where we have the intersection point. So we need to find once again the intersection point. Shift G solve, intersect, and here we have, it is worth $10,000, 10,000 UK pounds here when the boat is 4.27 years old. Okay, so that's what I'm going to write here. If we go back to the assignment, I'm going to write this. Let me copy the instructions. So using GDC, graph boat function, find intersection point. We're doing exactly the same thing here. So we get that the value of x is 4.27 years. That means that in the fourth year, and probably a little bit less than 4 months later, the boat will already be worth half its original value, okay? So that's how we solve exponential functions, and that's how we use also calculator to solve these types of problems. So I hope this was clear enough for you. If not, please let me know, and we will be clearing these doubts during future live sessions. See you.